Hello and welcome back to the course on artificial intelligence. And finally, we're on to the fun stuff. We're on to deep Q-learning. All right, so let's have a look. Previously, we spoke about Q-learning and what it's all about. And we learned about the agent, the environment, and how the agent will look at the state he or she is in, take an action, get a reward, enter into a new state. And based on that feedback loop, they will continue taking actions and they'll learn from that, understand what are the better actions to take. And so we looked at this basic example of a maze. We understood that as the agent explores the environment, it understands what the values of the states are. Then we moved on from dealing with the values of the states to dealing with the values of the actions or the Q values. And then based on that, we understood how plans in non-stochastic environments work and how policies work in stochastic environments. And this is an example of a policy. So that's a quick recap of everything we discussed in the basic Q-learning. And now let's have a look at how this can be taken to the next level through deep learning, through adding deep learning. Okay, so this is our environment. And what we're going to do now is we're going to add, instead of just doing basic calculations in this matrix that we have, which is pretty simple, what we're going to do is we're going to add two axes. We're going to add an X and Y axis, or we'll call them X1 and X2, just to make things even more general. And here we've got we'll number the columns 1, 2, 3, 4. Here we'll number the rows 1, 2, 3. And so now every single state can be described by a pair of two values, x1 and x2. So any one of these squares in which the agent can possibly be in can be described by x1, x2. So for instance, right now he's in the square with x1 equal to 1 and x2 equal to 2. And therefore, that's in that same way, we can describe any square, meaning we can describe any state. And of course, this is a very simplified version of an environment of describing states, but nevertheless, it works in this case. And that means that now we can feed these states into a neural network. And by the way, here, I would just like to mention that at the end of the course, we've got annexes. We've got annex number 1 and annex number 2. In order to proceed successfully with this section, it's highly advisable that you check out annex number 1, which is on artificial neural networks, so you understand how they work, so that we don't have to delve into that here, and we can just use the benefits of the knowledge of how artificial neural networks work. And so we feed in this information on the state into a neural network, and then it will process this information, so x1 and x2. Depending on the structure of the neural network, it might have multiple hidden layers and so on. So that's something that you'll figure out in the practical tutorials. But at the end, we will structure in such a way that it spits out 4 values. And these 4 values are actually going to be our Q values. So the values which dictate which action we need to take. And further down in this tutorial, we'll see exactly how these Q values are used to decide which action is taken. But the main point here is that we no longer look at just this maze from a Q-learning perspective. We're now taking the states of the maze and we're feeding them into a deep neural network in order to get these Q values. And at the end of the day, we're still going to come up with an action. We're still going to understand what action we need to take, and we'll discuss all this in more detail. But the question right now is why? Why are we doing all of this? Why are we making things so much more complicated when that initial approach of Q-learning was working already? Well, the reason for that is the Q-learning was working in this very simplistic environment. And we're continuing to deal for now with this very simplistic environment in order to better understand the concepts. But at the same time, that simple Q-learning will no longer work in more complex environments. And we're talking about, for instance, the self-driving cars, which you'll be creating, or playing Doom, when the artificial intelligence is playing Doom, or other Atari games like Breakout, or even self-driving cars and more advanced reinforcement learning things such as like robots walking around and performing actions. In all those cases, basic Q-learning is insufficient, is not strong, is not powerful enough to be able to master those challenges. And just like we've seen in the deep learning course, if you've been in our deep learning course, or if you've done the annex sections, annex number 1 and annex 2, you will already know that deep learning is by far superior to any type of machine learning, let alone simple Q-learning. And that's why we're leveraging the power of deep learning here. So we're feeding in the information about the environment, as a vector of values, so in this case just 2 values, into a deep neural network, and then we're using that to perform the actions that we want to decide which actions the agent's going to take. So that's kind of like a high-level overview of why we're doing this. And now let's have a look at, in a bit more detail, at what happens to the concepts of Q-learning when we make this transition from simple Q-learning into deep Q-learning. So as you saw in the previous intuition tutorials, we had a slide like this, which is the foundation of temporal difference learning. This is the formula for temporal difference. And basically, so let's go through this. So basically, we had an agent who was in this state over here, which is indicated by blue arrow. And we were understanding how temporal difference works for this Q value of, for instance, going up. And so what we saw here was before. This is in the simple Q-learning, not the deep Q-learning. This is in the simple Q-learning. What we saw was before the agent had a certain Q value that he had learned about this action of going up. And so then he decides to take this action to go up. And right after he takes this action, he gets a reward for taking this action in this state. And that is that reward. Plus, now he can evaluate the value of the current state he's in, which is the maximum of all of the new Q values of the new actions he can take, A prime, in the new state S prime. And we multiply it by the decay factor of gamma. So that is essentially the new Q value, or kind of like the empirical Q value that he has just received for taking that action. And ideally, these two should be the same. So the Q value that he had in his memory about this action in this state, it should equate to the actual reward plus the gamma times the value of the state that he ended up in. And therefore, that's how we calculate the temporal difference. We take what he got after minus what he had in mind, what he was expecting. You subtract one from the other, and that's your temporal difference. And then you use your learning rate alpha to adjust your Q value, your new Q value by the temporal difference, but with a coefficient of alpha. So that is the essence of the simple Q learning. Now let's have a look at how it changes in deep Q learning. And so we're still going to work with this slide, but we're going to just see exactly what's happening. So in deep Q learning, the neural network will predict 4 values. As we saw in the previous slide, and as we'll see further down in this tutorial, the neural network will predict 4 values, or it might predict more values if there's more possible actions in a given state. But in this case, we know that there's only 4 actions: up, right, left, or down. And so the neural network will predict 4 of these values. So there will be no, in a deep Q learning situation, it's important to understand there's no before or after. And this is how we'll get to know this a bit better. So the neural network will predict 4 of these values. And it will compare not to what will happen after, but the neural network will compare to this exact value, but it was this value which was calculated in the previous step. So in the previous time when the agent was in this exact square, so let's say, I don't know, some time ago, the agent was in this exact square as well, and it calculated this value previously. So in the previous time, a long time ago, the agent calculated this value. Then the agent stored this value for the future. And now the future has come. So now he's in this square again. And now he's got these Q values, which is predicted. And one of them is for going up. So now what he's going to do is going to compare the predicted value of Q to this value which he had recorded from the previous time. And we'll understand exactly why this is important right now. So just important to understand here is there's no before and after in this specific square, this specific time. We're taking the Q value that he's predicted using the neural network this time, and we're comparing it to this value, which he had from the previous time. From the previous time he was in this square, assessing all of the situation. And, the previous time he actually performed this action. So there we go. Now let's have a look at how this all works out in the neural network and why is it like that. I know it sounds a bit complicated right now, but we'll break it down into simple terms right just in a second. So this is our neural network. We're feeding in the states of the environment into the neural network. It's going through the hidden layers. Then it's coming out with these outputs, Q1, Q2, Q3, Q4. In that specific state, these are the Q values that the neural network is predicting for the possible actions. Those are the Q values. So then we're comparing to target, and these targets is exactly, so if we go back here, this is the target. So this is the value that was predicted, and then, but also we know that we have a target from the last time we were in the square. We have a target for this same action, which is up, for instance. So here we've got a target, and we're going to compare. So we're comparing Q1 versus that target. We're comparing Q2 versus that target, the target that we had from previously, Q3 versus the target, Q4 versus the target. And so this is the part where the neural network or the agent is now learning through deep learning how to better go through this maze. And the key point here is that we're still applying Q-learning, but the concepts in simple Q-learning, you learn through temporal differences, which are pretty straightforward, which we've already discussed and we know quite well by now. But at the same time, in deep learning, how do neural networks learn? Well, neural networks learn through adjusting their weights. So we have to adapt the concepts of the concepts of simple Q-learning to the way neural networks actually work, and that is through updating their weights. And so this is what we're trying to figure out here. How do we adapt that concept of temporal difference to a neural network so that we can leverage the full power of neural networks? And so far we've gotten this. So we enter our environment state here as a vector, goes through a neural network, we get predictions of Q values, and then from the previous time the agent was in that state, we have these Q target 1, 2, 3, and 4 for each of these respective actions. And so now we're up to, okay, let's compare each one with each one. And from here, it becomes pretty straightforward if you're up to speed with neural networks. Once again, that's all in annex number 1. We're going to calculate a loss, which is L here, and we're going to be Q target, this one, minus Q, minus this one. We're going to square that, so the square difference of each one of these, and we're going to sum them. So we're going to take the sum of the squared differences of these Q values and their targets, and we're going to sum them up, and that's going to be our loss. And so ideally, just as we had in the temporal difference learning, so if we go back for a second, remember we said, ideally, we want this to be equal to this. So we want the temporal difference to be 0. So that means basically the agent is predicting exactly correctly what, the Q values that the agent is predicting are exactly, or that he has in memory, are exactly descriptive of the environment. And therefore, the agent can navigate the environment pretty well, right? There's no surprises. There's no, as long as this temporal difference is highly positive or highly negative, then we've got some surprises. But if the temporal difference is 0, then he knows the environment so well that he can predict what's going on, and therefore his policy is going to be very good, and he's going to be able to navigate it. So here, same thing. So we want this loss to be as close to 0 as possible, as small as possible, and that's why now this is the part where we are going to leverage the real true power of neural networks. So we're going to take this loss and we're going to use backpropagation or stochastic gradient descent to take this loss and pass it through the network. Pass it back or backpropagate it through a network, and through stochastic gradient descent, update the weights of these synapses in the network. So that next time we go through this network, the weights are already a bit better descriptive of the environment. And that's exactly how it works. So here you have, if we go back, this is calculated, loss is calculated, and it gets propagated for the network. The weights are updated. Then the next time we get here, this happens again. And we get here, this happens again, and so on. And it keeps happening, and that's how this agent learns, or basically now it's a neural network, which is the brain of the agent, is learning, is becoming more and more descriptive of the environment, and therefore the agent is able to navigate the environment better. When we say descriptive environment, basically means that when we put in the states of the environment that the agent is in, we are more likely to get closer and closer to the actual Q values. And that happens because the Q values that we want and find the right action. And that happens because these Q targets are actually empirically derived. So how does he find these Q targets? That's actually this. So he actually observes, okay, so once I do take this step, what's the reward I get? And then what's the value of this state? So same thing as we saw previously in Q-learning, in the simple Q-learning intuition. So he learns this through trial and error. And then he constructs his network or updates the weights of his network in such a way that the predicted Q values are closer and closer approximating the target Q values. So very similar to the concept we discussed here in the simple temporal difference learning of the simple Q learning algorithm. So there we go. That's how the agent learns. So we're up to here. That's the learning part.